Hello everyone! Thanks for joining this second add-on video about algorithms. In the first one we discussed key value searching algorithms, which uses key comparisons heavily. Moving to the next topic for key value searching without keys comparison. Remember our analogical example of predefined places on a shelves, when you don't need to spend time and search by comparable keys in order. You immediately point to the right place instead. This idea is even more efficient than a logarithmic time search with comparable keys, and it is based on so-called hash table. To implement such hashing idea, items are generally saved in a key-indexed table. Access to the table by index is direct, one-step process. But there is a trick. Key is not always an integer value, while index of a table is. So we need to calculate index from a key. That brings new term hash function, which is a method for computing table index from a key. Why do we calculate table index? The main goal is just to quickly find a place to store or search some items in a table. Similarly to quick choosing shelf and bin in my room, index of a place, by type of item, my key. Similar to calculation in my head for mapping between key and index. How to calculate integer index from a key? It should be an agreement based on type of key and certain calculation rules. There are some recommendations, but for now keep in mind it can be any formula. For example, if key is a date, you can sum up all digits of a day, month and a year. Next, remember we are in a realm of key value searching task. So generally we need to store both a key and the corresponding value at a calculated index. So later we can find value by key. But why not to store just value and save space by not storing key? Just think, if we need to place value at certain index, key would help to calculate the same index, since calculation is for the same key using the same hash function when you search later. Why to save key along with value in a table then? Two tricky things to keep in mind when answering this question. When hash function computes index from a key, it generally squeezes potentially large key to a smaller integer. It is important to realize that usually there is no way to restore key back from calculated index. How you can restore date from an integer from our previous example. So when you put value without saving key, you later may need to get this value by key. If you are not storing key, you assume that if key pointing to index, it will lead you to index pointing to your initial key. It may work only in case each unique key points to uniquely mapped index of a table. In reality, hash function calculates index, and calculation is dependent on incoming key itself, which is not known prior calculation. So you cannot predict indexes calculated upfront. What if two different incoming keys may result in the same index calculated? Is such collision possible? Look into example of our hashing function taking date as a key. Making small change in the date, having another unique date, but with the same calculated index. So we have collision example, when you need to store potentially two key value pairs in the same place within a table. Returning to question, can we skip saving key? Since you cannot generally restore initial key by calculated index, you can put value for one key and later search for another key which could point to the same index due to potential collision. Do you think it gives trustworthy search results? Of course not. We need to be sure that we return value for only corresponding key. Therefore, we need to store both key and value. Size of a table better to be no smaller than number of key value pairs in attempt to minimize collisions. Imagine what you will have otherwise. There will be surplus of key value pairs to be inserted once table is already fully occupied. Collisions are unavoidable. Next, even if key value pairs are less in number than table size, hashing function might not be good, and with lots of empty space in a table it may still bring collisions, because calculation formulas are imperfect. Good idea is to find better formula so hashing function could evenly, uniformly distribute key value pairs to minimize collisions, or at least to make it even. for example 1-2 maximum collisions per any table index. Algorithm lecturers could share recommendations how to make it more effective, how to find trade-offs between considering the whole key value for index calculation, which might be costly, with just part of it. But collisions could happen anyway, so they need to be handled somehow. We need to implement collision resolution mechanism. Choose algorithm and data structure to handle 2 or more keys that hash to the same table index. One of the possibility, not the only one though, is to implement separate chaining symbol table. Idea is you need to use array of linked lists. Hash function should map key to integer within the size of such array. For example, if you have table with 100 items, hash function can return index value from 0 till 99 for any key. To insert, we need to put, if not already there, key value pair in front of a chain at calculated index. Searching requires to search within just one chain, once index is calculated. Here you can visually see that if your hashing function is imperfect and leads to preferring certain index over others when distributing key value pairs, then certain linked list will be lengthier than others. Again, our goal is to have uniform distribution of key value pairs, so length of all chains should be almost the same, without such spikes. Why do we need to reach such goal? Is it important? Oh yes, it will bring guaranteed performance, which is for example in focus of avoiding disaster consequences for mission-critical applications, like aircraft control, pacemaker, vehicle-to-vehicle communication, nuclear reactor, and so on. Each time you have such spikes in linked list length, your performance may significantly go down for both put and get methods, when your hash function for certain keys is landing to such lengthy linked list. But if implementation is good, hash tables are in general faster if compared with balanced search trees. Unleash your imagination. In our red-black binary search tree, to find a value, you may search keys from root till tree leaf, with logarithmic order of growth. For hash table, in practice you can reach with total just 3-5 order of growth steps on average, regardless of input data size, for uniform hashing of course. Oversimplified, you need to calculate index by key, first step, and with even uniform distribution, with average small 1-2 key value pairs at each index, you return or insert value nearly immediately. Another important comparison: balanced search trees support ordered symbol table operations, when you can compare keys. Hash tables do not allow you to compare keys. It's not embedded into their idea. And as of now, there are no effective alternatives to hashing to implement symbol tables for unordered keys. And one more comparison for you. Balanced search tree has stronger performance guarantee, logarithmic without any assumptions. Hash table is generally faster for simple keys, so we have just few arithmetic operations instead of log n compares for a tree. But average 3-5 steps are not guaranteed. In the worst case, even for uniform hashing distribution, it may be a log n order of growth. Surprising situation may be for non-uniform hashing. And even denial of service attack can be seen when somebody learns how your hash function works and put all key value pairs into a single table index. In our prior birthday example with simple hash function, we can insert carefully selected keys pointing to the same index. That may result in our performance to be halted. That was all about key value searching, related to symbol table abstract API. First category, when keys were subject to order and comparison. We discussed in the previous add-on video, where we finished with red-black binary search trees. Current topic about hash tables was for the second category, when keys are not in order. Hash function is to compute table index from a key immediately pointing to a specific place in a table. Collisions are possible when two unique keys point to the same index. One possibility out of a few to handle collisions is to implement separate chaining symbol table. For hash function, goal is to have evenly, uniformly distributing key values among all table indices. With uniform key distribution, we can achieve average constant 3-5 steps order of growth, which outperforms balanced search trees in lots of situations. Just FYI, another possibility for handling collisions, which was not mentioned in this video, is linear probing. Please read about it at your convenient time. That's it for hash tables. Before we finish overall key value search topic with Symbol Table API, let's discuss Symbol Table API in connection with specific key type. Large chunk of tasks nowadays are about search with particular data type, string search. Each string is well-known defined data type and technically is a sequence of single characters. Keys can be of so-called primitive data type for our key value search topic. Or remember our video about data structures. Examples of primitive data types are integer number, real number, character, etc. Values of primitive data type are atomic, indivisible into parts. But string, in contrary, is composed of smaller parts, characters. When computer compares strings, it compares symbol by symbol, one after another. If compares string beautiful with string beauty for search and purpose, computer should make 5 steps while checking similar prefix beaut, and only on the 6th step it will make an outcome that there is a search miss, because letter I is not equal to letter Y. Imagine that you have symbol table with lots of key value pairs, where keys are strings. The larger the total number of pairs, the more chances to have lots of keys having same substrings. For example, starting with the same prefix like predefined, prefrontal, preamble. When you search, there might be a lot of search misses before you could find a string. And for each string, computer will spend several steps for each string, even when some of them are with the same prefix. Is there any way to have algorithm and/or appropriate data structure which would allow us to combine efforts and spend several steps not for each single string, but for group of strings at a time? Like evolution of pharma tool plow. At the beginning, plow was able to make one length trench in one run, and later it was modified to make several trenches in one run. Within the last 2 topics, we were in the realm of abstract symbol table API, dealing with key value pairs. Adding and searching is done by a key in this structure. Now we will be focusing on string search. The key should be of type string. Value in the meantime may be some auxiliary, not necessarily always important for operations. For example, just a bit value, which to be set to 1 when new string is added into our symbol table. Or maybe integer value, storing number of search attempts once key value pair is added. Abstract string symbol table structure was introduced. Instead of generic key type in symbol table API, specific keys of type string to be used. For example, there are 2 main functions of generic symbol table API: put to put key value pair into the table, and get to retrieve value paired with key, may return null if key is absent in a table. They are to transform to specific functions of string symbol table API. Let me provide few use cases where searching by key of a type string would be very useful. Prefix match. Find all keys in symbol table starting with a given prefix. Examples: autocomplete in a cell phone, search bar, text editor. Action is user types character one after another at a time. Result is system reports all matching strings. Wildcard match. Wildcards used in so-called regular expressions, short way to provide a rule for string search. In our example, wildcard dot represents any one letter. Combination of symbols dot, h and e represents a rule which could bring list of such strings like she, the, etc. A longest prefix. Find longest key in a symbol table that is a prefix of query string. For example, for the word shell sort, shells is the longest prefix among few, like she, shell, shells. Another example, to send packet toward destination IP address. Router chooses IP address in a routing table that is longest prefix match. Additional use case, efficient spell checking, and it brings task to design data structure for such checking. For abstract string symbol table API, special efficient real data structure was introduced, named Trie. Trie outperforms in most cases both balanced search trees and hash tables. Let's briefly look and clarify by unleashing our geometrical imagination how such performance is achieved. What is the main design idea underneath Trie? How it might be more efficient for string search? And how exactly can we use idea of a revolutionized farmer plow when your computer still needs to compare symbol by symbol within each string? The idea of Trie is to step away from traditional full string storage, but to aggregate and store just one common prefix for several strings where possible. For our predefined prefrontal preamble words, we can store a common prefix pre and 3 separate leftovers, defined frontal amble. It sounds promising, but how Trie structure would look like? First of all, there is a generalization of Trie structure. The full name you could see in literature may be multi-way trie or R-way trie. R stands for radix or character set, where radix is a maximum number of unique characters in your set. For example, English alphabet contains 26 unique symbols, so radix R is equal to 26 in this case. Let's look to the main properties of Trie. Structure of Trie represents a tree with nodes. The main idea of Trie is not to store keys, which are full strings, but to store characters in nodes instead. A root node of a Trie does not contain any character. Each node has R children, one for each potential character. For example, for English alphabet, each node will have R equals to 26 children. If you don't have certain character inserted yet on a Trie level, it represents a null link, meaning absence of the corresponding character. For simplicity in our examples, we can omit and not draw null links, but remember that we reserved memory spot for it, and this time pointing to null value. So our Trie may look this way. When you add full meaningful string in your Trie, you add several characters corresponding to single key. Part of them could be reused from other strings prefixes. Characters are added one by one from the root towards the leaf. When string is added, we stored key. But what about value for our key-value pair? The rule of thumb, we should store value at the node containing the last character of our string. Value at certain node actually points to the place where string ends. If added string contains any meaningful substrings, each such substring considered added to Trie structure only and only when a node with the last symbol of substring contains value. For example, we can add key shells with value 3, and later can add key she with value 0. Only after adding value 0 at the node with the symbol E, key value pair she 0 considered added. Similarly, we can add word shell sort and word shell. Now let's quickly look how use cases we mentioned earlier can be effectively implemented using Trie structure. Prefix match, to find all keys starting with a given prefix. We need to realize that prefixes are unique in Trie structure. You cannot find two similar prefixes. Why? Because of the nature of Trie structure. Because prefix is at the beginning of string, starting from symbol number 1. Do you remember we discussed trees earlier in this video and mentioned level of tree? Nodes belong to the same level if they are at the same distance from a root. On the first level of Trie, we have only first symbols of any string. On the second level, second symbols are, and so on. If we look for prefix pred, it starts with letter P, and letter P, if was added, can be only one. It cannot be duplicated, since we reserve memory for all symbols just once, one node per each potential symbol. When we go to subtree with root P on the second level, it also can have non-duplicated symbols, and so on. If prefix exists in a Trie, it's unique and it was added for at least one string, so we could find one or maybe more strings starting from such a prefix. In our case for prefix pred, we need to apply so-called traverse operation to visit nodes underneath our prefix in its subtrees. Nodes to visit according to certain rule, each node to visit one time. Don't forget, prefix itself might be a complete string with value, not in our example though. In our case, we have strings: predict, prediction, predicate, and predator. Very convenient. Once you found prefix, just visit subtrees underneath. No need to search the rest of trie, regardless how large it is. That was about prefix match use case. For wildcard match, we just need to understand on which place of a string any symbol is to be. Involve your geometrical imagination and correspond symbol place with trie level. If first symbol is to be any, like in our .he case, we need to see are there any strings which start with any symbol and continue with he in our trie. We just need to check any potential case one by one on corresponding level. Check with first symbol A, if any, following by he. Then with first symbol B, if any, and so on. If wildcard is somewhere in the middle, you will start with prefix search, our prefix task, but wildcard will be applicable to different trie level, not the first one. Longest prefix is a very natural use case. Longest key in a symbol table that is a prefix of a query string. When you found string in your trie, you know all symbols belonging to this string, on the way from root to the very last symbol. If any other string which is substring was added to the trie, it should have value added for the node corresponding to the last symbol. All that you need to do is to find the largest one, if any. For our shell sort string, we have several other substrings added to trie. Strings she, shell, shells. The largest is the one which value is the farthermost from the root, but closer than value of the original string shell sort. So we have shells in our case. And another use case, data structure for efficient spell checking. This is just a kind of dictionary with all legitimate words of English language in 26 trie, where 26 is the radix of English alphabet. Here is how it may look like. When you misspell word, put wrong symbol in certain place, we can suggest one or several legitimate words from our dictionary with wildcard for one or several places in the word. That was about use cases implementation ideas. Important thing to pay attention regarding trie: search does not need to go all the way to the bottom. It can terminate at intermediate node. Another important thing, we have performance guarantee for tries, log n characters accessed in the worst case. Do you see difference? Not log n strings compare operations, but log n characters. And remember, lots of strings are partially aggregated by their common prefixes, bringing extra economy to our search. That's how tries could be more efficient than balanced search trees and hash tables. In literature, you also can see term ternary search tries. Let me briefly show the difference. It can be considered as different representation of multi-way or R-way trie, but solving the same tasks of our abstract string symbol table API. Main idea to introduce this trie variation is to have economy on null links, which we were not showing for tries, but they actually exist in real implementation. Ternary search trie, TST, also has characters and values in nodes, but implemented the way that each node has just 3 children, with smaller characters on the left, equal in the middle, larger on the right. Not 26 children, as in our previous example. Each TST can have equivalent representation of R-way trie. What we are losing with TST is simple 3-layer structure with first symbol of any string to be on the first layer, second symbol to be on second layer, and so on. TST has simple rules to move left, right, center though. The obvious gain that we have with TST, significantly less null links, which is more space efficient in case our radix is large enough. For example, Unicode, 2 octets characters, and so on. Let's wrap up content of these first 2 add-on videos to why algorithms. We discussed a large key value abstraction topic with 2 important methods: insert value with specified linked key and search for corresponding value by a given key. We gave few use cases where such abstraction is useful, like DNS lookup, dictionary, etc. Two categories of search options were mentioned: when key is compared for search purposes and when keys comparison is not used for searching. Remember wall with the service window, which we discussed in the previous video, What Algorithms? The wall which separates abstract API from a hidden real implementation. Our abstract symbol table API's two main functions are put, with parameters key and corresponding value, and get, taking a key and returning value. Even though such API looks very simple, implementation behind the wall might not be so intuitively simple. It might be specific type of tree structure, red-black balanced search tree underneath, which is perfectly balanced, having the same black link length from root to any leaf node, or implementation might be using hashing idea by calculating place on a shelf by a given key. This idea brings collision possibilities when more than one key could point to the same place. So collision resolution mechanisms were implemented, like chaining symbol table, for example. At the very end, we discussed symbol table API, namely string symbol table API. And implementation involved Trie structure, tree-based structure which stores characters instead of keys, full strings. All these implementations are for the purpose of the most effective optimal performance, to make it faster than any other competitors. Hope you enjoyed this add-on video and ready to watch extra about graph structures and relevant algorithms. See you!